Hi folks, I'm back with component 3. I think this better be component 3. Again, I'm going to have a go at this without sort of having seen it before, so I can't guarantee that my answers will be absolutely correct. This is not about me giving you a perfect mark scheme. It's hopefully about me trying to talk you through the method that I'm going to use. So without further ado, let's get stuck into question 1. Is my pen working? Oh gosh, it's gone well already. State the amplitude of the wave. So notice this is a state. No calculations are required. Amplitude is maximum displacement. So 2 is the answer here, but do be careful with the units. 2 micrometers. Calculate the wavelength as precisely as you can from the graph. Now notice it says calculate, it doesn't say state. So that kind of gives us a clue, because you can read a wavelength off the graph. It's from there to there, for example, is a wavelength. But this says calculate as precisely as you can. So for maximum precision, what we would want to do is, instead of measure a single wavelength, measure some wavelengths and do a calculation. So if I just check where this peaks, you'll only ever have to do this to the nearest grid line. So that is the third minor grid line in from that end. 1, 2, 3, 4 minor grid lines in from that end. And then just check on the scale. What have we got here? This is 0.5. That is 20, is it? So each one of these, each minor grid line is 0.025. Is that right? Could that possibly be right? Yeah, it is. So that's yeah, all good. So 3 in there, that is 0.075. 4 in from that end is 0.1. Is that correct? I think it is. So that's at 2.4. So my calculation then, that is a total of 1, 2, 3 wavelengths. So my calculation is going to be 2.4 minus 0.075 over 3. And I should have had a calculator at the ready, and I haven't. I do apologize. Let me just grab a calculator here. 0.775 meters. I'm going to leave it to 3 sig figs. I'm not going to round it. It says as precisely as you can. And given that these minor grid lines are here, I think the same number of decimal places in my answer is fairly appropriate. So, using the graph to explain how the phase of the wave varies with distance, in your explanation include the terms in phase and in antiphase. Now, I wonder, is it kind of okay to label this graph up? Yeah, I wonder. There's 4 marks here. So the first thing I guess we probably need to say is that phase changes with distance periodically. And the periodicity of that is 1 wavelength. Because in this case, we're talking about how phase varies with distance. So as we move along the wave, the phase of the wave is varying. It is periodic. So it is going through this sort of repeating cycle. And then I think we need to, because it says use the graph, and we should include terms in phase and in antiphase. So for example, this is where I wonder, can you actually go ahead and label this up? Can I just label some points on the graph? I don't know. So I could like label point A, point B, point C, point D, E, and F. And then I could say A, C, and E are in phase with each other. Similarly, B, D, F are in phase with each other. Since they're a whole wavelength apart, I suppose you could add to that. And then A, C, E are in antiphase. With BDF. And I kind of feel like that's probably enough. Not sure about, I think that's okay. It says use the graph. I've used the graph. I've labeled some points on it. I think that's probably all right. It will be worth a look in the mark scheme. Maybe the mark scheme is going to want you to refer to actual positions using the distance scale or something like that. I think possibly I might add in that these are in phase with each other and lambda apart. And ACE are in antiphase with BDF since they are lambda over 2 or lambda over 2 or 3 lambda over 2, 5 lambda over 2 apart. Something along those lines. Okay, I suppose you could have put in a more general, couldn't you? Anyway, let's move on. I feel like I'm doing this quite slowly. I do apologize. Displacement time graph then for a point on the wave. So this is the SEM wave. Specifies that here. So it is the SEM wave. But now we're looking at a time against displacement. So the amplitude remains the same. But now we're looking at how a single point varies over time. Calculate the speed of the wave as precisely as you can. So here, the first thing we need the frequency or the time period. And the way I think I'm going to go about this is pretty much exactly what I did before. Now, this starts here at -1. So here is a full wavelength. There is another, full cycle, not a full wavelength. There is a period, there is a period, there is another period. And I'm going to divide that by 3. So being really careful with my scale, I'm kind of struggling to see this on my screen. 1, 2, that looks to me like 6.8 milliseconds. So 6.8 times 10 to the -3. Again, just be ever so careful with scale. I think if I've labeled that up, it's really clear to the examiner, whoever's marking this, what I've done here. I've labeled these points on my graph. I've shown very clearly where I've got this from. And I'll divide that by 3. I feel like I could probably have done this one in my head. 2.27 times 10 to the -3. Seconds is the time period equals time period. Speed, C equals F lambda equals lambda over T. So I can't remember what the wavelength was. 0.775. Check that in my calculator. 341.9, so 342 meters per second. That feels like an easy 4 marks, to be honest. I mean, it's taken a bit of time. You've got to, and there is a point to be made here. Given that the calculation was straightforward, That is an easy 4 marks, but remember, if you're aiming for a little more than a minute per mark, do take your time. Make sure that you've checked the units for the skill that you're reading. Make sure that you have correctly read the point off the graph. It is frightening how often good students make errors just reading graphs. Explain the value of the displacement when the time is 8.7 milliseconds. So 8.7 milliseconds, explain the value of the displacement when it's 8.7 milliseconds. So 8.7 is off the end of our graph here, which is awfully disappointing. So what we can do is at 6.8, the displacement is -1. So one possible method, at 7 exactly, the displacement is 0. One possible method, we could do 8.7 minus 7 equals 1.7. So 1.7 milliseconds after passing through 0. After 0 displacement. And then we can just look at somewhere else on the graph where that is true. So 1.7 milliseconds after 0 displacement, therefore same displacement as at, well, this passes through at 0.2 milliseconds, so at 1.9 milliseconds. Arguably I could put in t equals, maybe I'm going to put in t equals 1.9 milliseconds. Because it does say explain, it doesn't say calculate, it says explain, and then let's just read it off the graph. At 1.9, displacement is minus 1.9 micrometers. As far as I can see, is it though? No, it's -2. My eyesight. -2 micrometers. And yeah, that's it. I'm happy enough with that.